Hello and welcome to the session of flash loading. So in the previous video we have seen how the bootloader works and how the bootloader jumps to application. Okay, for doing that we have understood what the vector table is and why, if there are multiple applications, each application has its own vector table assets offset, and when the vector table offset is set, you also need to set the main stack pointer accordingly. Okay, and why the reset handler is at the very top of the stack. So this is a brief recap. Okay, so once you have gone through the previous video, you will be ready to understand what is flash loading. Okay, so this session was on somewhere around January end, but this documentation was generated on February 8th. All right, so we are going to learn the STM32 flash loader protocol. Now, in the previous video, we have only seen bootloading, but we have not seen how the bootloader also has a capability to write into the flash, right? But we are going to enable that feature also via UART. So there's a custom UART protocol we are going to write that is going to read in bytes, and then we are going to send the bytes into the flash memory. How we are going to achieve it and how we are making sure that we are doing so in an error-free fashion, okay, will form the rest of this series. So at the end, you might see a surprise demo, like we will be able to flash the STM32 over the air or Wi-Fi using the custom firmware update over the air that we are going to implement over the same protocol. So this flash loading protocol we will use over ESP32 also, and also using a Python script for the desktop. Okay. All right. So let us understand flash, the flash peripheral on the STM32, before we see how the loading is done. So if you see this page on embedded flash memory, that is from the reference manual of the STM32 F1 series, you can see that the flash memory is split into pages. Okay, a page is just a logical division, but there are 32 pages or 64, up to 64 pages of 1 kilobyte each. Right. So it depends on the type of device, the low density device and medium density device. But for the F103, it's pretty much clear. You have page size of 1 kilobyte, and there are 64 such pages. Okay, that information is in the data sheet. But for the purpose of this video, we will refer the reference manual and understand that how the flash is really split into pages, and this is ignoring the system memory and option bytes, and each page is 1 kilobyte, which means your application must fit in 1 kilobyte ranges. There is no in between. Okay, and there are certain registers involved when you are accessing or reading and writing into the flash from the HAL itself. Usually either the JTAG interface or the internal boot ROM has access to these, but we can unlock the flash, write something into it, okay, and lock the flash again. Okay, so the idea of flash loading is the ability to write into these pages. Okay, but one thing to remember is just read this section. So the programming and erasing of flash memory, we can only do it 16 bits or half words at a time, and you have to do the erase operation at the page level, which means that you cannot delete individual bytes. The entire page you have to erase and flash at the same time. So just if you read the manual for some time, you will get to know how the flash is structured and what are the basic things that we need to do before we write a flash loader. All right, so let us get this out of the way and observe that how the flash organization is there. This is from our notes. We have 64 KB of one page. Okay, one page has about 1 KB, 64 pages. All right. So the bootloader is taking the 8 KB. All right. And we can have an extended bootloader, and the rest of the pages we are dedicating it to the application. So this is very important because you really need to know what is the exact size of your bootloader. That is how you reserve space for your application, and you can make your bootloader as lightweight as possible. Okay. So the main HAL API that we are going to use is HAL flash unlock. Okay. By default, the flash is locked after reset for data integrity and safety. So there are certain flash keys that you will get from the data sheet, the default flash keys that we have to provide in sequence. Once you do that, your flash is in an unlocked state and you can erase or program. And post that, you can safely lock. So in a typical bootloader, what we are going to do is we are going to find out how many pages we are going to erase exactly. All right. And then we are going to lock and unlock each page at a time. Okay. And we have an erase time and we have a write time. And this is very critical because flash is a capacitive circuit. Therefore, it takes time for the voltage to settle. So there are certain APIs like HAL Flash Program API that is provided by the ST itself. You can also do the same bare metal, but for the purpose of time, let us see that if you are trying to take a 128 byte chunk and write it, first you need to erase the whole page. Okay, and then you need to write one half word at a time. So that is how you are going to do it. Looks simple, but to orchestrate it and to meet the timing requirements, that is a challenge. Okay, so really there's only one way of doing this. You unlock the flash, you do some operation, either erase or program, and then you lock it back. Okay, so the complete example is provided in the notes, and we are going to see it in the application also in the code. But since this is clear, we will now describe our UART based flash loading, like how we are going to take the chunks coming from the UART and put it on the flash. Okay, since we have understood the flash layout and the number of pages, let us come to our problem statement. I have a bootloader that is taking the first 8 kilobytes of flash, and the bootloader has a UART protocol, so which it has the capability to accept incoming bytes, and now it has to push these bytes over to the application region here and start writing one by one. Now it's not necessary that you write all 56 KB. 56 KB is available, but we really need to make sure that the pages are written in order and the buffering is done properly. So the idea is each page is exactly 1024 bytes, 1024 bytes. So you can have your buffering mechanism set up like you know your page, you know your block number. This is pseudocode, but you know your page, you know your block number, and you know your buffer size. Your buffer is the number of bytes coming from the UART at any point of time. So if you multiply your buffer size with the block number, it should come up to 1024. So which means that for each page, you are dividing the page itself into a number of blocks. And each block contains a 128 byte payload coming from the UART. Okay, so that is how we are going to frame. That is how many chunks we are going to send. So each UART transmission will contain 128 bytes split over 8 blocks. So 128 into 8 will give us one page. Like that, we can have 0 to 56 pages based on the application size. So this is our flashing strategy. This is our flashing strategy. Next, we will look into the actual flashing protocol. Before you move on, it is absolutely imperative that you understand UART and the UART baud rate and the UART 8N1 protocol. If you don't, please pause the video and come back. Due to time constraint, I won't be covering UART here, but it's absolutely essential that you have basic understanding of what UART is. Okay. So since we have our strategy set, let us understand the UART flash loading sequence diagram. Now, the reason I'm showing sequence diagram first and not the code is because to really understand the flow, it's better that we visualize it first. Okay. Now, some of you might be expert, like you can just look at the code and understand what is happening. But it's very difficult to get an intuitive feel of any protocol just by looking at the code. That's why, we have standardized UML diagrams. And one of the UML diagram is the sequence diagram. So here we have three participants. One is the host, the bootloader, and the flash memory. This host can either be your PC with a Python script, or it can be an ESP32 or any other device that has UART enabled. Literally any device that has UART enabled. I am describing the protocol flow. First, the STM32 needs to be powered on, and we have seen in the previous video, it will send a boot message. All right. Now, the moment you send the boot message, I want to send a C character to select my CRC. Now, it's just a character. It can be a starter frame, anything, but I simply want to say that please start my transmission. Okay. So the bootloader will decide and acknowledge if it's ready to get the bytes from the host. Okay. Now, once the acknowledgement happens, the host starts sending the payload. Now, this payload is nothing but a sequence of bytes that we are going to see. This is inspired by the XModem protocol. It's not exactly XModem protocol, but hear me out. We are going to send the start of header, which indicates that the payload starts from this particular point. And in the same frame frame is basically a grouping of bytes. We are going to send which block number that we want the data to appear in. And then we are going to send a complement of that block number just to be safe. So there's a comparison operation that will take place. So you're writing into the correct block number and nothing has been corrupted. And you are going to send the data along with a CRC. Now CRC is used in protocols to ensure the data integrity, which means that during the course of this transmission over the wire, you don't have any bit flips happening. Now the CRC at most can handle 1 or 2 bit flips. Okay, but it's still useful tool. Modern algorithms use AES or CMAX or cipher based message authentication codes. Now that's a big thing. But for a short wire distance, and if you are okay with your retrying, this CRC method works well enough. Okay. So at the end of the data transfer, another acknowledgement is sent. Okay. To check the integrity of this data. That's where the CRC comes in. If the CRC is valid, like if the CRC computation is same on both the host and as well as the microcontroller, now you know that all the data has been sent as is. Okay. Only then the data writing to flash happens. Okay. And even before this, the flash needs to be unlocked, but I'm not putting everything in the sequence diagram. And after all the block transmission happens from the host side, there is an end of transmission, which signals to the bootloader that there won't be any further bytes coming. Once this is done, the flash write is finalized. That is, the flash is locked. and a final acknowledgement goes, and this session, UART session, is ready to terminate. Once this final acknowledgement is there, you know that you are ready to jump to the application. Optionally, if you spend too much time waiting for the initialization message from boot, also it jumps to the application. Ultimately, jump to the application will take place under two circumstances. Either you successfully flashed, or you were waiting for a flash and it didn't happen, or in case of a error handler or the flash is not configured properly, it will go and jump back to the bootloader so that you can retry again. Okay, just go through this segment, go back and go through this segment slowly. I've tried my best to explain, but sometimes looking at the code might also give you certain clarity. So next we are going to walk through the code of how this happens in the bootloader, and similarly the same using a simple Python script. Now I'm also assuming that some working knowledge of Python you will have. Okay. Otherwise it's a very simple protocol even from a Python standpoint. Okay. So this is the point where you can stop, pause the video and go back on the concepts like UART and Python and serial ports with Python using PySerial. Okay. Okay. So if you have gone to the description of this video and download the JIT, okay, so you would have seen these 4 folders come up. Now let's understand the folder structure before we go into the code. I've also made it a little bit simpler while I was recording this video because the CRC concept might be a little bit complex. So I just replaced it with a simple checksum. But since the code is available, you are free to extend it as you want. Okay. So there are 4 folders you will see. First is the actual bootloader itself that we have already discussed in the previous application video, but this contains the flash loading code along with the bootloader code. Okay. Next we have the scripts folder, which contains the simple test scripts and actual flashing scripts. Okay. This is a simple serial monitor to check if my UART is working properly or not. And this is a flash loader. Next is the ESP32 application, which does the FOTA. So this is quite complex, but you can go through it. It will take more than one video to cover the contents, but we'll see a demo. It contains a website that will open up on the ESP32 and will allow you to read the flash. Okay. So next is we have our actual application that we want to flash. It's a simple application. You can replace this with your application, but just make sure your linker file is accordingly, that you start after the 8 kilobyte bootloader. If you can make that change, you can flash whatever application you want with this bootloader. Okay. So understand the previous video and this video and you'll get why that offset and vector tables are needed. So let us go and check the code one by one. It's very simple. We just need to look at 2 files in this. First is, let us see the simple bootloader main.c. Okay. So already there's some documentation. So what we are going to do is we are going to define our protocol macros, okay, or the commands that are going to be sent. So SD are actually ASCII printable UART characters. For the ease of debugging I'm using, you can replace them with non-printable characters. Okay. So S will start the command to fetch the bytes from the host. And when the data packet is being sent, the prefix will be starting with D. And once the transfer is done, we will have a E or end. So all this is making sure that how we are making that UART frame. or the series of bytes. Okay, so we have a buffer of 1 KB. I already explained you why this is, because we are writing and erasing one page at a time. Our buffer size should also be 1 KB. Okay, and certain functions we have to send bytes on the UART, to receive bytes, and a simple checksum. You can use a CRC. If you use a CRC, you need to do the same CRC calculation on both sides. Okay, the STM32 also has a built-in CRC peripheral. Okay, but we are not going to use that. For the sake of simplicity, I just use a simple checksum. Okay, so let me check the actual logic. Now this is the check application valid function. So when you write into the flash, you just need to make sure that your RAM address and your base address is starting correctly. This is just a boundary check. Okay, this is a checksum. Now we discussed the previous using CRC, but it's the same. CRC and checksum are both mechanisms to ensure data integrity. For the sake of simplicity, I just used a checksum here, but you can also use a CRC because the STM32 has a CRC peripheral. Okay, now this is a flash write page function that wraps over the HAL APIs. So again, we are going one page at a time. What we are going to do is, first we are going to unlock the flash. This is most important, flash unlock. And there is a sequence to unlock this that the HAL unlock command does for us. Okay. Next, we are going to erase the page, and then using a for loop till the complete size of the data is flashed, we are going to iterate. Now the same is mentioned in the documentation PDF provided, and then we are going to lock it. Once this is done, so this will be invoked as part of the flash loader process. This is not the complete process because this is only for one page. There might be more than one page involved as part of the flash loading, right? So this is the master for loop, or I can say while condition, that sets up this handshake procedure that we have discussed in the sequence diagram. And a copy of the sequence diagram is also present along with the source. Okay, this one. More or less we are doing this, just replaced CRC with the checksum. Remaining everything else, this is the state machine that we are implementing. This is a sequence diagram that we are implementing. Okay, it's included as part of the GitHub package and also in the session notes. So this is the message we'll be seeing. So in the previous video, we observed that the bootloader continuously sends a boot message for 5 seconds. Within that time, if you are able to capture this message on the host, you can start your transmission. Now there is only receive logic because the STM32 bootloader will receive data from the host. Now in the host, there will be framing and packet sending logic that we are going to see. Okay, so after all the handshake happens, and as part of the debug also, there are certain debug mechanisms. I have debug prints, but make sure your debugging is over a different UART channel than the one you're trying to flash. Here it is the same, but when you are implementing, ideally your debug channel and your flashing channel should be different. I might fix this for in the later revision. Okay, so that's it. This code is an implementation of the sequence diagram that you have seen on the STM32 side. But on the host side, we have a Python scripts. Let us take a closer look. I go to scripts and I open simpleflash.py display. You see, I have the same protocol implemented here, and I know the commands I need to send SDE. So as per the diagram, as per the sequence diagram, we'll try to just put it side by side, hopefully, and we can compare. Can I disable the sidebar? Yes. So go to the flash loader. I have this protocol. So I hope it's reasonably visible. I'll just get myself out of the way. Nice. So we need to check for the boot message first, that is coming from the bootloader. That is what is happening here. So once we receive the bootloader message, after power on, we mark the variable boot found as true. This is Python. This should be reasonably easy to follow. Otherwise, it's very simple. It's just a series of functions with a loop to do this handshake. Okay. And these timings are very important because of the flash retention. After you send your bytes, you need to wait for the flash write to settle. Okay. Otherwise, it will fail. So I've put pretty conservative delays here. Okay. You can optimize for your application. So once you receive your boot message, you are going to wait for another C character. Okay. So once you receive the C character, you are going to start sending the frames one by one. Here in the diagram, I'm showing XModem frame protocol with a CRC, but I'm sending the same with a checksum. Okay. So here I'm going to create my chunk. Okay. And I'm sending my chunks 8 bytes at a time. 8 bytes at a time, which means that each page will contain 128 chunks. All right. This is what the logic we have discussed. Okay. So we cannot send the entire 1 KB buffer at a time. We can send, but the bootloader should be able to write immediately in the buffer. That's why we are sending in chunks, so that even if some chunks are malformed, we can retry with the checksum check or the CRC check. Okay, so 128 into 8 is 1024. So we are sending 128 chunks of 8 bytes. All right. After that, the serial .flush commands will do the actual transceiver send. And then what we are going to do is we are going to wait for the acknowledgement message. If we receive the acknowledgement message, we know that we are good to go for the next chunk. So each chunk waits for its own acknowledgement message here, this ACK. Or it can be an NACK if the CRC or the checksum fails. Okay. Now after certain retry, we can fail the entire process. Or if it succeeds, we can complete sending all the bytes and send the end of transmission, EOT. So the EOT or the command end is sent from the host. Okay. After that, there is a final acknowledgement that all the flash writing has happened. Now, immediately after this, the firmware transfer will be marked as complete and the bootloader will jump to the application. Okay. Go back and refer to this segment or just read through the code. Both the codes, the bootloader code and the flash loader, are the implementation of this sequence diagram. The host implements the Python script and the bootloader implements the C firmware in the STM32 that does the actual flash loading and jump to the application. Okay, so we have the firmware from our older session. Okay, so I just hooked up a logic to serial port analyzer. Okay, so let us see what bytes it is outputting when we click on reset. So you can see the data coming, that is boot, and then we see the jump to application. I'll just pause the data capture and let us see the physical bytes coming on the bus. So we know that the bootloader is active and the bootloader is able to jump to this address here. Okay. So this is a sequence of bytes. I think this is a boot message, BOT. Okay. Similarly, we should also be able to see the chunks when the bootloader is sending bytes or the flash loading is happening and the bootloader is receiving bytes from the flash loading application or the Python script. Okay. If this font is small, I'll try to zoom in, but you can see that the message appears, boot message appears along with a jump to the application. Now let us try to invoke the simple Python script, simple flasher Python script, and let us see the sequence of bytes. In order to invoke the simple flash loader that is written in Python, we need to first flash the bootloader. That is done via stflash command. Okay, it's already done, so I'm only just resetting the chip. Now this will only work if you have a JTAG. Okay, but since we don't have a JTAG connected and we only want to jump and to the directly bootloading the flash loading the application, we can just invoke the Python script over the USB. Okay, now this is TTY USB is the actual FTDI connector where your connection is. It on Windows it can be COM1, COM2 or COM3. On Linux it can be TTY USB 0 or 1. Okay, but this is the interface. Afterwards we are giving the file. This is the bootloader file that we want to flash, but in reality I want to flash the application one. Okay, so let me go to the path and just check this. It's called app1.bin. All right, this is the file I want to flash. I'll copy the path. All right, so this is the path to the application I want to flash. And before that, let me see if this flashing happens. I'll just put my controller in reset mode and then click on this. It will detect the bootloader and it will start sending in the chunks. Okay. Now this application simply contains the LED blink. We can test it by having a different application that blinks over a different LED or a different frequency, but it will flash and work. So now let us see how the UART protocol is working, how the bytes are being sent during this. For that, let me change the logging port to the transmission. Previously we were listening on the reception. Now we are listening on the transmission from the host side. Okay, I'll run this to on one side. Here I'll bring up my terminal, reset my board and start. You see the entire chunks are being sent. And this is how the transmission is taking place. After the transmission succeeds, we can pause it and we can see that we are sending 8 bytes at a time. Okay. So this is what is a one chunk, 8 bytes. 1, 2, 3, 4. So the E6 is a start of header. E6 is the start of header. And then F8 is the end. What the 8 bytes in between, okay, are the data. And one of them, FB, this is the CRC bit or the checksum. So we start, we give the block number. So if you see the next frame, it should be 84 or yeah, it's incremented by some offset. But generally this 8 bytes in the chunk, one of them is the checksum, the last one. So we have a start of header, we give the block size, we send the byte and we pack the checksum along with it. So this is how the transmission is taking place. We start the communication, we send the bytes, we pack the checksum. So 8 bytes are sent in 128 chunks. So if you see this gap, before that there are 128 transmissions. So 128 into 8 is 1 KB. So from this timeline, this entire timeline is 1 kilobyte of data sent. All right. Okay. So I have the ESP32 demo ready. Basically, there is a application written in the ESP32 that implements the same protocol. All right. So this protocol is the same as the Python script. You can see that we are sending 8-byte chunks. The command starts with S. There's a data, there's an end field, and we are also sending the checksum. Okay. So how it works is there is a cyclic task that takes in a bin file, okay, or a hex file. If it's a hex file, it will convert it into a bin file, and then it will start sending the commands in sequence. I've connected to the ESP32, okay, via the IP. Let me get this out of the way here, and let us flash. Already I've tried flashing, so there's file present for me, application.bin. Now I'm going to reset and I'm going to flash. It is waiting for the bootloader. There might be some issue with the wiring here and there, but if it receives a valid bootloader, it is going to start flashing. Okay, it has completed flashing. So if you want to see the logs of what happened in the background, we need to connect to the ESP32. Okay, so the ESP32 is also connected via serial port. Let us connect to that serial port first. So sudo mini. Okay, it is connected over Dave TTY USB 1 device. Okay, connect. Okay, so I'm going to invoke, put this in the side, and I'm going to invoke the flash loading again. I'm going to reset and I'm going to flash. So it is going to detect the bootloader. Okay, and then it is going to flash it. Let us try one more time. I'm going to reset my STM32 and I'm going to say flash firmware. It is going to send the chunks and it is going to transfer. Then it will jump to the application. So this is how you can do firmware over the air updates with an ESP32. The code is available. It's based on Arduino. So if you just take a look at it, it's easy to explain because already it's implementing the same protocol that is there in the Python file. Okay. Thank you.